Another characteristic, that is the resistance. Everybody knows what is a resistor. A resistor is an element. If some voltage is applied across that, it provides the current start flowing through it. But that material means connected across the voltage source provides some hindrance in the flow of the current. So that hindrance is nothing but it is proportional to applied voltage and current flowing through it, and it is a constant, and that constant is termed as the resistor. So this is known as the resistivity of the material. Correct? Now, so like capacitor, inductor, resistance is also a characteristic of a material or device. It depends on both the material and geometry of the resistor. The material itself can be characterized by specific resistivity, and that is expressed in terms of rho, which is defined as the ratio of E to J, its current density. Okay. So to find the resistance R, we can take the help of these two expressions, and it can be expressed as rho into L by A, where L is the length of the element, A is its cross-sectional area, and rho is the specific resistivity. Okay. This ratio L by A is called the geometry factor. So thus, if one wants to design a resistive sensor, he or she should find a way of modulating, means altering either the specific resistivity or geometry factor of the resistor. So by changing its geometry or the value of rho of material, one can design a sensor that is based on the sensing resistivity of material. So that can be designed which senses the resistivity of the material. Correct. Now, the in real sense, the specific resistivity or conductivity of material is not constant. Practically, it's not true. Theoretically, it may be. So it changes with temperature T, and that change may approximately be linear. But if we look into a narrow range, then it may be linear. If we look into wider range, it may not be linear. Okay, so this changes with temperature, and in a relatively narrow range, may be linearly approximated as given by this expression: rho equals to rho naught bracket 1 plus alpha T minus T naught by T naught, where rho naught is the specific resistivity at reference temperature, room temperature T naught. In general, it is 25 degrees C. Okay, so at room temperature, specific resistivity of material is represented by rho naught. Now, when the resistivity of material depends on the temperature, and this alpha that comes in the expression, it is known as the temperature coefficient of the resistor. Okay. In broader range, this specific resistivity is non-linear function of temperature. As we can see from this figure, for material tungsten, the temperature sensitivity is plotted, means the value of rho versus temperature. When temperature is increased, its resistivity increases, we can say roughly linearly, but it's not actually linear, but roughly linear. Okay, so it is changing with temperature. So when a resistor is used in electronic circuit, its resistance shall be as temperature independent as possible. So that type of resistor, we will say a good resistor. So tungsten is always considered as a good resistive material. So a good resistor may have alpha, means the temperature coefficient of the order of 10 raised to power 5, or even lower, means its value should be negligible. If it is negligible, then see what happens with this expression. Alpha times whatever is there, that can be approximated very small as compared to 1. So rho is always equals to rho naught. So at every temperature, it is same. So it is independent. So if alpha is very small, it will termed as a good resistor, and that is in fact desired for electronic circuits. Means every electronic circuit that we are using, resistor must be a good resistor, capacitor must be a good capacitor, inductor will also be a good inductor. So good inductor, good resistor, good capacitor means their resistance must be independent of all the environment parameters. Similarly, capacitance, similarly inductors, but practically it is not true. But the things are totally opposite in case of sensor technology. It is often desirable to have a bad resistor whose temperature coefficient of resistivity, that is alpha, is high and predetectable. Means alpha must be very high and we can detect in advance, means how much value it will have. So a strong alpha allows to fabricate a temperature sensor known as thermistor. So this is one example of temperature sensor. It's known as the thermistor, also termed as resistive temperature detector, RTD. The most popular RTD is platinum temperature sensor, which operates over a broad temperature range from about minus 200 degrees C to 600 degrees C. The resistance of platinum RTD is shown in this figure. Now look at this. This is what resistance in ohm, and this is the platinum. So now if we look this line, temperature changing from 10 to 100 degree. Now if we look at this, the resistance of platinum, although it is not constant, it is changing from 100 to, let's say, 200 something ohms. If temperature changes by an amount of 100 degrees C. But still, it is considered as a good RTD. Now, now what happens when we have platinum resistive material? We want to design this a good sensor. Okay, but what happens in this? The resistance of this material changes with temperature. So, if temperature is different, its resistance will change. That will be because of the temperature, not because of the stimulus. So we cannot exactly correlate, or we cannot exactly observe which type of stimulus in which amount is present. Okay, so for that some compensation mechanism may be there. Now, for a calibrating resistance, the best fit state line, actually don't go in the detail of this, but we can see thermistors or the RTD. These are the example of pump sensing elements. They can be designed using tungsten, using the platinum, etc. etc. So the thermistor are resistors with large either negative temperature coefficients or positive temperature coefficient. What does it mean? The thermistors are resistors whose resistances may change in positive direction when the changes in temperature occur, or in negative direction. So that's why they may have either negative temperature coefficients or positive. Means the value of alpha may be negative, may be positive. So what will happen? R will not remain R naught that was at the room temperature 0 degrees C. So that may be less than the R naught or maybe more than R naught. Okay. So by this, what we can see, what we can get the advantage from that. We can sense the temperature of environment. We can sense the temperature of the space where this type of material is present. So that can also be used in the sensors to sense the temperature. So the thermistors are ceramic semiconductors commonly made of oxides of one or more of the following metals like nickel, magnesium, cobalt, titanium, iron. Oxides of other metals are occasionally used. Resistances of thermistors vary from a fraction of ohm to many mega ohms. Okay, thermistors can be produced in form of discs, droplets, tubes, flats, or thin film deposited on ceramic substrates. Recent progresses in thin film technology allows us to print thermistors on ceramic substrates. So resistances of semiconductor may be controlled to create either NTC means negative temperature coefficient or positive temperature coefficient to form a semi-conductive RTD. Now see what I want to explain with this temperature sensitivity. The specific resistivity or conductivity of material is not constant. Correct? It changes with temperature. And if we look into a relatively narrow range, then it may be linear, means resistivity remains same. But in broader range, it's not linear. Okay. So this resistivity, special resistivity of material depends on temperature. Okay. And it may be approximated through alpha. The alpha is termed as temperature coefficient of resistance. Okay. As we have seen in earlier expression. What was the earlier expression? On this one, just a minute. It's rho equals to rho naught 1 plus alpha times T minus T naught by T naught. Where this rho naught is the specific resistivity at temperature T naught. That is room temperature, either 25 degrees C in Kelvin, in degrees C, and or we can say absolute zero temperature. Correct. So this is the room temperature. Now in broader range, resistivity is non-linear. So it's not linearly related with this. So it can be expressed like alpha something T plus something alpha 1, then T square, then alpha 2. So rho can be expressed as rho naught plus alpha T means I'm talking about this expression alpha T minus T naught by T naught. Let it be delta T. Okay. So how we can express this rho resistivity as rho naught plus alpha times delta T plus alpha 1 times delta T square plus alpha 2 times delta T cube, etc. etc. So that can be approximated by a nonlinear expression in broader range. Okay. Where the expression contains T as it is represented as temperature in degree C, and rho is the resistivity of material in ohm meter. Okay, so there are few metals, they have positive temperature coefficients, means alpha may be positive for them. While many conductors and oxides, they have negative temperature coefficients, means alpha will be negative for these materials. So as I said, when the resistor is used in electronic circuits, the alpha must be very, very low. Even it should be always close to zero. So then that resistor will be termed as a good resistor, and we can use that type of resistor in electronic circuits. So alpha is zero, means resistivity of the material will not depend on the temperature, it will remain constant. But in sensor technology, it is often desirable to have a bad resistor whose temperature coefficient of resistivity is high and predictable. Okay, a strong alpha allows to fabricate a temperature sensor known as a thermistor. So if we have material for those alpha is very high, then what we can do, we can design a sensor. Okay, and that type of sensor is known as thermistor. A general name is associated with this. Thermistor can also be termed as the temperature detector, the resistive temperature detector, RTD. So we can design a sensor known as resistive temperature detector that can detect the temperature based on its resistivity. Okay, so if temperature changes, resistivity of that resistor will be different. So we can design a sensor. For that, we have considered one example. Okay, so to sense this temperature with the help of material, maybe platinum, maybe tungsten, etc., etc. Based on what? Its resistivity depends on temperature. What we want to do, we want to sense the temperature variation. So if there is any change in the temperature, what will happen? Its resistivity, if it is having a positive temperature coefficient, resistivity will increase. If it is having a negative temperature coefficient, its resistivity will decrease. R0 is the resistivity or resistance of the particular material at room temperature. So if there is increase or decrease in the temperature, the resistance of material will either go up from R0 or will go down. So by measuring that, we can correlate if this much of temperature, because of this much of temperature difference, the resistance changes from this value to this value. So we can sense the temperature. Okay. And how these materials can be constructed. So it is mentioned here. These materials, because their resistance depends on the temperature, so they are not pure resistors, they are semiconductors. Okay. And how they can be constructed? Based on some oxides or oxides of one or more metals like nickel, magnesium, cobalt, titanium, iron, etc. So depending on different oxides of materials, we can construct these type of RTD to sense the temperature. And the resistance of these semiconductors can be controlled to create either negative temperature coefficient or positive temperature coefficient. So if temperature is increased, the resistance of the material increases, means they have positive temperature coefficient and we can control it. Control means in the sense we can sense. Okay. So if there is variation in the temperature, we want to sense that variation, we can design a thermistor that is having positive temperature coefficient of resistor. So by sensing that variation, we can sense the variation in the temperature. So this is mentioned in this slide. Now, so what we have discussed, the temperature, the capacitor, inductor, resistor. Capacitor, it senses the electricity. Correct? Inductor, if we want to sense something, so the phenomena may be related to the mutual inductance, mutual coupling, or the magnetic. Okay, so by sensing the magnetic characteristic, we can say this much of inductor is present, and we can design some sensors based on the inductance, based on the variation in the inductance, etc., etc. Now, this is based on the resistor.